Hello students, in our previous class we learned about matrix. Okay, that means what is the definition of a matrix and some definitions, some more definitions related with a matrix. Okay, like diagonal element, diagonal matrix, unit matrix, null matrix, etc. Okay, so in this class we will learn how we can form a matrix. Okay, that means formation of a matrix. Okay, so in our previous class we learned about the general form of a matrix, which is matrix A equals to A11, A12, A13 continuing A1n, A21, A22, A23 continuing A2n, like this way continuing, and the last row is mth row and its elements are am1, am2, am3 continuing amn. This represents that the matrix A has m rows and n columns. Okay, already you know this general formation of a matrix. In a shorter way, we can also represent this matrix A by this form. Matrix capital A equals to Aij within first bracket m by n, where I equals to 1, 2, 3 continuing up to m and j equals to 1, 2, 3 continuing up to n. Okay, so this is the shortest representation of a matrix. Of a matrix. Already we know null matrix. This is the example of a null matrix. This is also another example of a null matrix. Generally, null matrix is denoted by the alphabet O. Okay. Generally, null matrix is denoted by the alphabet O. So, with the help of this notation, we can write this as O 2 by 3, because this null matrix has 2 row and 3 column. This as O 2 by 2. Because this null matrix has two rows and two columns. This null matrix has O 3 by 3 because this null matrix has 3 rows and 3 columns. Okay, so these are some shortest, this is the shortest way of representation of a matrix, and this is the representation of a null matrix. Okay, now we will learn how we can form a matrix. Okay, form a 3 by 3 matrix where Aij equals to I plus j whole divided by 2. Okay, we have to form a 3 by 3 matrix where Aij is equals to I plus j whole divided by 2. Already we know Aij represents an element of a matrix which lies in ith row and jth column, where this element is related by this general form. Solution. Since the required matrix is of the order 3 by 3, so its elements are A11, A12, A13, A21, A22, A23, A31, A33, sorry, A31, A32 and A33. Okay. Since we have to form a 3 by 3 matrix, so that required matrix is of the order 3 by 3 and its elements will be in the form A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. Since Aij equals to I plus j whole divided by 2, therefore A11 equals to 1 plus 1 whole divided by 2, that is 2 by 2 equals to 1. A12 equals to 1 plus 2 whole divided by 2 equals to 3 by 2. A13 equals to 1 plus 3 whole divided by 2, that is 4 by 2 equals to 2. A21 equals to 2 plus 1 whole divided by 2 equals to 3 by 2. A22 equals to 2 plus 2 whole divided by 2, that is 4 by 2 equals to 2. A23 equals to 2 plus 3 whole divided by 2 equals to 5 by 2. A31 equals to 3 plus 1 whole divided by 2 equals to 4 by 2 equals to 2. A32 equals to 3 plus 2 whole divided by 2, that is 5 by 2. A33 equals to 3 plus 3 whole divided by 2, that is 6 by 2 equals to 3. So the required matrix is A11, A12, A13, A21, A22, A23, A31, A32, A33 equals to A11 means 1, A12 means 3 by 2, A13 means 2, A21 means 3 by 2, A22 means 2, A23 means 5 by 2, A31 means 2, A32 means 5 by 2, A33 means 3. So this is the way by which we can form a matrix. Okay. So in this problem, Aij is equals to I plus j whole divided by 2. By following this relation, we find all these elements of the required matrix. They are A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay, and then replacing this value in this form, we get this required matrix. Okay. Now we will learn equality of matrices. That is when two or more matrices will be equal. Okay. So when for two matrices their order and their corresponding elements are also, that means same position elements are equal, then we can say those two matrices are equal. That means if order and same positional elements of two or more matrices, if ordered and same positional elements of two matrices are equal, then we can say that the matrices are equal. Okay, that means if we choose two matrices, two matrices and their order and their same positional elements are equal, then we can say those two matrices are equal. Okay. Example, if capital A equals to 1 square, 2 square, 3 square, 4 square, and capital B equals to 1, 4, 9, 16, then the order of then the order of matrix A is 2 by 2 because it has 2 rows and 2 columns, and order of matrix B is also 2 by 2 because this matrix B also has 2 rows and 2 columns. Okay, so first of all, the order of these two matrices A and B are equal. A11 equals to 1 square, that is 1. A12 equals to 2 square, equals to 4. A21 equals to 3 square, equals to 9. A22 equals to 4 square, equals to 16. Here A11, A12, A21, A22 represents elements of this matrix A. B11 equals to 1. B12 equals to 4. B21 equals to 9. B22 equals to 16. Here the elements of matrix B are represented by B11, B12, B21 and B22. They are 1, 4, 9 and 16. So A11 is equals to B11. A12 is equals to B12. A21 is equals to B21. A22 is equals to B22. Implies that matrix A is equal to matrix B. Okay. So if order of two or more matrices are equal and their corresponding elements are also equal, then we can say those two matrices are equal matrices. Okay. Here we choose a problem. In this problem, we have to find x, y, z and t when these two matrices are equal. Okay. So if we observe these two matrices, then their order are equal. Order is 2 by 2 because it has 2 rows and 2 columns. Order of this matrix is also 2 by 2 because it has also 2 rows and 2 columns. Since solution. Since the given matrices are equal, therefore x minus y, z plus t, y minus t, x plus z is equal to y minus z, 2 plus t, x minus z, 3 plus y. This implies their same positional elements are equal. So x minus y is equals to y minus z, y minus t is equals to x minus z, z plus t equals to 2 plus t and x plus z equals to 3 plus y. Okay. Since these two matrices are equal, So their same positional elements will be equal. That is, this is the element whose position is A11. That is 1 1. First row elements of first row and first column. So and this is also elements of first row and first column. That is why x minus y equals to y minus z. Y minus t is equals to x minus z. Z plus t equals to 2 plus t. X plus z is equals to 3 plus y. Okay. Now from this relation we get z equals to 2 plus t minus t. Cancelling this plus t minus t, we get z equals to 2. From this, we get x equals to y minus z plus y. So x equals to 2y minus z. Since z equals to 2, we can put 2 in place of z. That is why x becomes 2y minus 2. From this relation, x is equals to 3 plus y minus z. X means 2y minus 2, 3 plus y, and z means 2. From 1 and putting z equals to 2. Cancelling this plus 2 and minus 2, sorry, plus 3, z will minus 2. Cancelling this minus 2 from both sides, we get 2y minus y is equals to 3. So y is equals to 3. Okay. So x is equals to 3 plus y minus z. Again x is equals to 2y minus 2. That is why we replace this by 2y minus 2 and then z equals to 2. So cancelling this minus 2 from both sides, we get 2y minus y is equals to 3. That means when this y in the right hand side comes in the left hand side, it will be minus y. That is why 2y minus y equals to 3. So this will give y equals to 3. So z is known, that is 2, y is also known, that is 3. Now putting y equals to 3 in 1, we get x equals to 2 into 3 minus 2, that is 6 minus 2, that is 4. From this relation, we have y equals to 3, x equals to 4, z equals to 2. This will give minus t equals to 4 minus 2 means 2, and when this 3 goes in the right hand side, then this will be minus 3. So minus t equals to minus 1. Multiplying both sides by minus, we get t equals to 1. So therefore x is equals to 4, y equals to 3, z equals to 2, and t equals to 1. Okay. So this is the way by which we can find the values of unknowns when two or more matrices are equal. Okay. Now we will learn when we can add two or more matrices. Okay. Addition or subtraction is conformable between two or more matrices when their order are equal. Okay. Addition or subtraction is conformable between two or more matrices when their order are equal. That means we can add elements of same positions. That means we can add same positional elements of two or more matrices when their order are same. Okay. So addition and subtraction is conformable between two or more matrices when their order are equal, and we can add or subtract same positional elements of these matrices. Okay. Example. Suppose A is a matrix 2, 3, 5, -4, x, 3 plus y. B is another matrix 0, 5, -2, 1, -3x and 5y. Okay. So solution. Order of matrix A is 3 by 2 because this matrix A has 3 row and 2 column. Order of matrix B is 3 by 2 because this matrix B has 3 row and 2 column. So order of these two matrices A and B are equal. That is why addition and subtraction is possible between these two matrices. Okay. Since their order are equal, so addition and subtraction between these matrices is possible. or conformable. Therefore, A plus B is equals to, A means 2, 5x along first column, 3 minus 4, 3 plus y along second column, plus matrix B is equals to 0, minus 2, minus 3x along first column, 5, 1, 5y along second column. Now we have to add same positional elements. This is element of first row and first column. This is also element of first row and first column. This is element of first row and second column. This is element of first row and second column. 2 plus 0, 3 plus 5. This is element of second row and first column. This is element of second row and first column. 5 plus into minus 2. This is element of second row, second column. This is element of second row, second column. This is element of third row, first column. This is element of third row, first column. This is element of third row, second column. This is element of third row, second column. Two plus 0, 2, 3 plus 5, 8, 5 plus into minus 2, that is 5 minus 2, minus 4 plus 1, that is minus 3, x plus into minus 3x, that is x minus 3x, 3 plus y plus 5y, 2, 3 minus 2x, 8 minus 3, 3 plus 6y. Okay, so here we add same positional elements of matrix A and matrix B. Now A minus B along first column 2, 5x, second column 3 minus 4, 3 plus y, minus of along first column 0, minus 2 minus 3x, 5, 1, 5y. Similarly, we have to subtract between same positional elements of these two matrices. 2 minus 0, 5 minus of minus 2, x minus of minus 3x, 3 minus 5, minus 4 minus 1, 3 plus y minus 5y. 2 minus 0 means 2. 5 minus into minus 2, that is plus 2. X plus minus into minus 3x, that is plus 3x. 3 minus 5, that is minus 2. Minus 4 minus 1, that is minus 5. 3 plus y minus 5y. 2, 5 plus 2 means 7. X plus 3x means 4x. Minus 2 minus 5, 3 plus y minus 5y means minus 4y. So this is the way by which we can add or subtract uh, between two matrices. Okay, that means addition and subtraction of two matrices are possible only when their order are equal, and we have to subtract or add same positional elements of these two matrices. Okay, now we will learn addition is associative as well as commutative. Okay, now we will prove addition is commutative as well as associative. To check this, we choose two matrices. They are 7, 8, 5, 4, 1, -2. B equals to 3, 1, 2, -1, 0, 5. Okay. Now A plus B equals to, the order of these two matrices are 3 by 2. That is why addition is possible between these two matrices. So A plus B is equals to 10, 6, 3, 7, 4, 3. Similarly, okay, I will explain this elaborately. 7 plus 3, 5 plus 1, 1 plus 2, 8 plus into -1, 4 plus 0, -2 plus 5. This will give 10, 6, 3, 7, 4, 3. B plus A is equals to -1 plus 7. Okay, first of all we write matrix B 3, 1, 2, -1, 0, 5. Then matrix A along first column 7, 5, 1, 8, 4, -2, 3 plus 7, 1 plus 5, 2 plus 1, -1 plus 8, 0 plus 4, 5 plus into -2. This is 10, this is 6, this is 3, this is 7, this is 4, this is 3. So A plus B is equals to B plus A, imply matrix addition is commutative. If there is another matrix C, say C equals to 11, 0, 4, 5, 6, 1. A plus B plus C. The order of matrix C is also 3 by 2 because it has 3 row and 2 column. So addition of this matrix C with A and B and their addition form, that is A with A plus B, is possible. That is why A plus B plus C. A plus B matrix means along first column 10, 6, 3. Along second column 7, 4, 3. Matrix C is 11, 0, 4, 5, 6, 1. So this will give 21, 6, 7. 21, 6, 7. Along second column 12, 10, 4. B plus C. B plus C means 3 plus 11. Along first column 1 plus 0, 2 plus 4, minus 1 plus 5, 0 plus 6, 5 plus 1 along second column. This will give 14, 1, 6, 4, 6, 6. A plus B plus C is equals to A matrix means 7 along first column 7, 5, 1. Along second column 8, 4, minus 2 plus. B plus C matrix means 14, 1, 6, 4, 6, 6 along second column. So this will give 21, 6, 7, 12, 10, 4. Therefore, A plus B plus C is equals to A plus B plus C, imply matrix addition is associative. Okay. So this is the way by which we can prove these two different properties. They are commutative property and associative property. Okay. So this is the way by which we can say, conclude that addition of two or more matrices is commutative as well as associative. Okay. Subtraction between two matrices is not commutative. So by the similar way, we can prove subtraction between two matrices is not commutative. That is, A minus B is not equals to B minus A. Similarly, for three matrices, we can say that subtraction is not associative. Okay. Multiplication of a matrix by a scalar. Say A is a matrix 3, 7, 5, minus 1, 2, 9, 4, 6, 8. Now 2A. Now 2A represents multiplication of matrix A by 2. That is the multiplication of all the elements of matrix A by 2. Okay. So here A is a matrix. Now 2A. 2A will represent multiplication of matrix A by 2. That is the multiplication of all the elements of matrix A by 2. Okay. So this multiplication is known as scalar multiplication. Scalar multiplication of a matrix. Okay. So after multiplying all the elements of matrix A by 2, we get 2 3s are 6. 2 into minus 1 will give minus 2. 2 into 4 will give 8. So along first column we have 6 minus 2 8. In the second column 2 into 7 14, 2 to the 4, 2 into 6 12. So in the second column we have 14, 4, 12. In the third column we have 2 5s are 10, 9 2s are 18, 2 8s are 16. So in the third column we have 10, 18, 16. Okay. So this is the way by which we can multiply a matrix by a scalar. Here scalar means some number or algebraic expression. Here as a scalar we choose 2. So when 2 is multiplied with matrix A, then we have to multiply all the elements of this matrix A by this scalar 2. Okay, and after multiplying all the elements of this matrix A by 2, we have this. Okay, so this is a way by which we can multiply a matrix by a scalar. Now we will learn multiplication of matrices. Okay, so when we can multiply two or more matrices. Okay, so first of all we choose two matrices. So after choosing them we have to study what is their order. Okay, so before multiplication before doing multiplication of two matrices we have to study their order. Okay, and if the number of column of first matrix is equal to number of rows of the second matrix, then we can multiply first matrix by second matrix. Okay, multiplication between two matrices. First of all we choose two matrices, that is why multiplication between two matrices is possible or conformable when number of column of first matrix is equal with number of rows of second matrix. Okay, so multiplication between two matrices is possible only when number of column of first matrix is equal with number of rows with second matrix. Okay, that is if capital A equals to Aij m by n and capital B equals to B Rs n by p, then AB is possible as number of column of matrix A, that is n, equal to number of row of matrix B, that is n. For this matrix A, number of column is n and for this matrix B, number of row is n. That is why we can multiply matrix A by matrix B. So AB represents multiplication of matrix A by matrix B. Okay. Again, number of column of matrix B, that is P, not equals to number of row of matrix A, that is M. So BA is not possible. Okay. So when number of column of matrix A, that is first matrix, is equal to number of row of matrix B, that is second matrix, then we can multiply matrix A by matrix B, that is AB is possible. Okay. And in this case, for matrix AB, the order will be M by P. That is when A equals to Aij M by N and B equals to B Rs N by P, then order of AB equals to M by P. That is, this common will remove. Okay. So this is the way by which first of all we have to identify multiplication between two matrices is possible or not. Okay. Now we will learn how we can multiply between two matrices when these conditions are fulfilled. Find the product of the matrices if possible. 3, 2, 5, -1, 7, 6. 8, 9, 8, 9, 1, 4, 11, minus 3. Here two matrices are given. They are matrix A equals to along first column 3 5 7, along second column 2 minus 1 6, and in matrix B along first column 8 4, in second column 9 11, and in third column 1 minus 3. So first of all we have to check multiplication between these two matrices is possible or not. Order of matrix A 3 by 2 because it has 3 row and 2 column. Order of matrix B is equals to 2 by 3 because this matrix B has 2 row and 3 column. So number of column of matrix A, that is 2, equal to number of row of matrix B, that is 2, implies that AB is possible. That is, we can multiply matrix A by matrix B. So therefore AB is equals to 3 5 7 2 minus 1 6, and matrix B is equals to 8 4 9 11 1 minus 3. Here we have to follow row by column method for multiplication. Here we will follow row by column method for multiplication between matrices, as it is a easier way of multiplication. Okay, there are so many ways of multiplication for two matrices. Here we will choose row by column method for the multiplication of these two matrices. That is, first of all we have to multiply the elements of first row by first column to get the first element of this new matrix. That is 3 into 8 plus 2 into 4. 3 into 8 plus 2 into 4 will give the first element of the new matrix. Then first row, second column. 3 into 9 plus 2 into 11. Then for the second element, that is element A12, we have to multiply the first row of this first matrix with the second column of this second matrix. That is why 3 into 9 plus 2 into 11. Then for the third element of the new matrix, that is for A13 of the new matrix, we have to multiply the elements of first row by third column. 3 into 1 plus 2 into minus 3. Okay. Then for the element A21, we have to multiply the elements of second row by first column. 5 into 8 plus minus 1 into 4. 5 into 8 plus minus 1 into 4. Then for the element A22, we have to multiply the elements of second row by second column. 5 into 9 plus minus 1 into 11. 5 into 9 plus minus 1 into 11. Then for the element A23 of the new matrix, we have to multiply the elements of second row of first matrix by the third column of second matrix. 5 into 1 plus minus 1 into minus 3. Okay. Then for the element A31 of the new matrix, we have to multiply the elements of third row of the first matrix by the first column of second matrix. 7 into 8 plus 6 into 4. 7 into 8 plus 6 into 4. Then for the element A32 of the new matrix, we have to multiply the elements of third row by second column. 7 into 9 plus 6 into 11. Then for the element A33 of the new matrix, we have to multiply the elements of third row of the first matrix by the third column of second matrix. That is why 7 into 1 plus 6 into minus 3. 24 plus 8. 40 minus 4. 56 plus 24. 27 plus 22. 45 minus 11. 63 plus 66. 3 minus 6. 5 plus 3. 7 minus 18. 24 plus 8. 40 minus 4. 56 plus 24. 27 plus 22. 45 minus 11. 63 plus 66. 3 minus 6. 5 plus 3. 7 minus 18. 32, 36, 80. 49, 34, 129. Minus 3, 8, minus 11. Okay, so this is the way by which we can multiply matrix A by matrix B. Okay. So this is the way by which we can find the product between two matrices. Okay. In our next class, we will learn how matrix multiplication is sorry. In our next class, we will learn either matrix multiplication is commutative or not. Okay, that means whether matrix multiplication is commutative or associative or not. Okay.